The objective of this video is to practice laying out a single layer fractional slot winding. In a previous video, we came up with a set of design steps that we follow to lay out a fractional slot single layer winding. And in this video, we are now going to practice using those design steps on this example. So the example problem is for us to design a single layer winding for a 72 slot, 30 pole, 3-phase motor. And the very first question of the example is to complete design step 1. And design step 1 of our design process is to determine if the winding is symmetric. So please go ahead and practice this on your own. See if the winding is symmetric or not, and then press play when you are ready to watch me do it. And so we've determined our number of slots per pole per phase so that we can get into this form of z divided by n. And then we use our value of n in this expression to see if it's an integer, which turns out that p by n is 3, which is an integer, and therefore this symmetry condition passes. And then our second symmetry condition is that n must be coprime with m, our number of phases, and 5 is indeed coprime with 3, so this condition passes as well. And we now know that this winding is a symmetric 3-phase winding. Next, I want you to determine the base winding size. Specifically, I want you to determine how many slots and pole pairs are in the base winding. This will help us determine our winding layout because, well, 72 slots is an awful lot of slots to draw, so we prefer to just consider this for a reduced number of slots, that is, our base winding. So press pause, give this a try, and press play when you're ready to watch me do it. Our first step in answering this question is to determine the values of q prime and p prime, where q prime is the number of slots it takes before our magnetic conditions repeat themselves, and p prime is the number of pole pairs it takes for the same to happen. And if you recall, the way we do this is we calculate t, which is the greatest common divisor of q and p, and in this case we find a t value of 3. And then q prime is simply equal to q divided by t, so it's 24 slots before our magnetic conditions repeat themselves in a coil side. And then p prime is equal to p divided by t, so it's 5 pole pairs until our magnetic conditions repeat themselves in a slot. And the next question is whether our base winding length is simply equal to q prime, or if we have to go around a second time. Do we need 2 stretches of q prime slots, or can we get by with just 1 stretch? And we answer that by determining the grade of the base winding. And we can determine the grade of the base winding by looking at whether n is an even or an odd number. In our case here, n is equal to an odd number, and we determine this above up here. We calculated our slots per pole per phase above, and we see that it's 4 divided by 5, which means that n is equal to 5, and therefore we have a first grade winding. And for a first grade winding, our base winding length is simply equal to q prime. And that's great. We much rather draw a 24 slot winding than a 72 slot winding. And p star is equal to 5, so that means when we do our phase zone diagram for our base winding, we only have to have it repeat itself 5 times instead of 15 times. So next, I want you to finish doing the remaining design steps, and we'll take this one step at a time. The first step is symmetry, validating that the winding is symmetric, and we've already done that, so that step is done. The second step is to write q in this form of being g plus z prime by n. And please go ahead and do this, practice it on your own, press pause, and press the play button when you are ready to watch me do it. So we find that we have a value of 0 plus 4 divided by 5, which is just our original q value because z is already less than n. So in this case, g equals 0, z prime equals 4, and n equals 5. Next, I want you to do design step 3, which has you determining how many coils are in your different coil groups. So please give this a try, and when you're ready to watch me do it, press play. And so here you can see that I have determined that we should have 4 coil groups with 1 slot, or 4 phase zones with 1 slot, or 4 coil groups with 1 coil. and one coil group with 0 coils, or one phase zone with 0 slots. And remember that we had this rule of thumb that this should alternate as frequently as possible. However, you can see from this it doesn't really make any difference whether you put this 0 slot phase zone in the middle up here or if it's on the end. This sequence is going to repeat itself, and so because there's only one slot that's different, or there's only one coil group that's different, it doesn't matter where you place it. Next, I want you to construct the phase zone diagram table that we introduced in our previous video on the design process, and do this for the base winding, and do the complete table that I worked in our example where we have the 2 additional rows on the bottom that indicate the number of slots in each zone, and then the slot number that starts a given zone. So press pause, give this a try, and press play when you're ready to watch me do it. And so here I've started constructing the table, and you can see that we've started labeling Q1 through Q5 on only the positive phase zones. And then when we get to Q5, our pattern repeats itself. So we do this, and we keep doing it for the entire base winding length. And remember, we'd previously determined that our base winding had 5 pole pairs, which meant that the sequence had to repeat itself 5 times until we get to the condition that W plus has the last sequence of our coil group. So we have 5 pole pairs, 1, 2, 3, 4, 5, which means that we cycle through this until we get to the point that Q5 is in our last position, which is our base winding. So remember, our base winding is the shortest independent length of our winding, so that our winding can be viewed as being several base windings connected together. And then we label the return coil sides. And finally, we label the slot number that is occurring at the start of the zone, because this will make it much easier for us to draw our winding layout schematic. And we notice that we finally end up using 24 slots, which matches our previous calculation that our base winding length should have 24 slots. Next, I want you to construct the winding schematic for phase U. And before you pause, I want to be clear that we want the winding schematic for phase U base winding, so it does not have to be the full 72 slots. All right, go ahead and pause the video and press play when you're ready to watch me do it. So we've got our 24 slots drawn below, and now it is time to determine where the phase U coils are. And this is actually a fairly easy task because we've indicated this information right here. So we can see that we've got a phase U coil right here, right here. We can go ahead and highlight these all the way across. And of this, you can see that this coil right here does not exist. We have no slots there. We have no slots in that zone. So coil 1 is going to connect slot 1 to slot 3. Coil 2 is going to connect slot 6 to slot 8, then 10 to 13, and then we are going to have 20 to 23. Until we finally have this winding layout schematic. And notice that the first 2 coils have a span of 2 slots, while the last 2 coils have a span of 3 slots. And we can see why this happened, because if you look at the table, you can see that in the first 2 coils, we skip a zone within their span. Well, in the last 2 coils, we do not skip any phase zones within their span. So, in summary, this video has gotten you to practice the design steps for laying out a single layer fractional slot winding. We've worked through the complete set of design steps, and finally we've constructed the actual winding layout schematic.